Okay, so we are working on more stuff for encryption. We're going to do public key infrastructure and cryptographic protocols. Okay, so first, digital certificates. This is a common application of cryptography. You use digital certificates, you understand to use them, you understand the purpose, know how they're managed, and determine what type of digital certificate is appropriate for different situations. So a digital signature is used to prove a document originated from a valid sender. The weakness of digital signatures, it can only prove that the private key of the sender was used to encrypt the digital signature. An imposter could post a public key under a sender's name, trusted third party, used to help solve the problem of verifying identity, verifies the owner and that the public key belongs to that owner. A digital certificate is a technology used to associate the user's identity to a public key that has been, quote, digitally signed by a trusted third party. So this is imposter public key, and it's just showing here's Bob's public key, here's an imposter public key, and here's Alice with the imposter public key. And it's just showing you what that would look like. Managing digital certificates. Several entities and technologies are used to manage digital certificates. Most common are certificate authorities. Tools for managing certificates. Certificate authorities are for if a user wants to use a digital certificate. After generating a public and private key, the user must complete a request with information such as name, address, email address, and known as your certificate signing request. Now, usually a lot of certificate authorities and CSRs, when you're dealing with this, you're either dealing with like websites or you're dealing with software. That's what they use a lot of these for. User electronically signs the CSR and sends it to an intermediate CA. An intermediate CA processes the CSR and verifies the authenticity of the user. Intermediate CAs are subordinate entities designed to handle specific CA tasks, such as processing certificate requests, verifying the identity of the individual. The person requesting a digital certificate can be authenticated by email, documents, or in person. A common method to ensure security and integrity of a root CA is to keep it in an offline state from the network. It's only brought online when needed for specific and infrequent tasks. Certificate repository is a publicly accessible centralized directory of digital certificates. It can be used to view certificate status. The directory can be managed locally by setting it up as a storage area connected to a CA server. Certificate revocation. Reasons a certificate would be revoked: if it's no longer used, details of the certificate have changed, like the user's address, private key has been lost or exposed, or it's suspected lost or exposed. A certificate revocation list is a list of digital certificates that have been revoked. And it's important to have that because sometimes these certificates, they post them and they have a good from this date to this date. And once you go past that date, you get put on that cert revoke list. And if you don't have those, then you can have these non-valid certificates floating around out there. And this is what certificate revocation list, what these look like when they're in their certificate trees. Online Certificate Status Protocol, OCSP, performs a real-time lookup of a certificate status. OCSP is called a request response protocol. The browser sends the certificate's information to a trusted entity known as an OCSP responder. The OCSP responder provides immediate revocation information on that certificate. OCSP stapling is a variation of OCSP where the web servers send queries to the OCSP responder server at regular intervals to receive a signed, time-stamped response. So this is your example of a web browser running through your web server to your OCSP responder. It says, I want to connect. Is it valid? And it's giving the approval steps that they use. Okay. Different types of digital certificates. The most common categories of digital certificates are root certs, domain certs, and hardware and software certs. Root digital certificates, the process of verifying a digital certificate is genuine, depends upon certificate chaining. Links several certificates together to establish trust between all the certificates involved. The beginning point of the chain is known as a root digital certificate and is created and verified by a CA or certificate authority. They're self-signed and do not depend upon a higher level authority, which is why they're called root. Endpoint of the chain is the user digital certificate itself. So as you can see, this is just an example of the chain. So at the top here, you have your Equifax root digital certificate, GeoTrust Global, and then you can see that they're going down to the different ones all the way out to the user digital certificate for that particular website. Domain digital certificates. Most digital certificates are web server digital certificates issued from a web server to a client. Web server digital certificates perform two primary functions. They ensure the authenticity of the web server to the client and ensure the authenticity of the the cryptographic connection to the web server. There are several types of domain digital certificates. There's the domain validation digital certificates, extended validation or EV digital certificates, wildcard digital certificates, subject alternative name or SAN digital certificates. And this is an example of what a key exchange looks like in that case. So you have your client hello, server hello, then it verifies and creates your pre-master secret, exchange, pre-master secret, and then you can see that they have those keys they create there. Hardware and software digital certificates. More specific digital certificates relate to hardware and software. There's the machine computer digital certificate, code signing digital certificate, and email digital certificate. Digital certificate attributes and formats. The standard format for a digital certificate is the X509. All X509 certificates follow the standard ITU-T X690, which specifies one of three encoding formats: basic encoding rules, canonical encoding rules, or distinguished encoding rules. And this is what it looks like with your digital certificate attributes. And as you can see, remember we were talking about algorithms. RSA is a encryption algorithm. Okay. Which of the following is the beginning point of a certificate chain? User cert, intermediate cert, root cert, top level cert. Look at that. Everyone's paying attention. Good job. Okay, public key infrastructure, PKI. So anytime you see PKI, that's what it actually stands for, is one of the most important management tools for use of digital certificates and asymmetric cryptography. It is important to understand PKI to know PKI trust models, how it's managed, and the features of key management. There is a need for consistent meaning to manage digital certificates. PKI is a framework for all entities involved in digital certificates. Certificate management actions facilitated by PKR created, store, distribute, and revoke. Okay, trust models. Trust is defined as confidence in or reliance on another person or entity. A trust model refers to the type of trust relationship that can exist between individuals and entities. Direct trust is a type of trust model where one person knows the other person. Third-party trust refers to a situation where two individuals trust each other because each trusts a third party. The web of trust model is based on direct trust. Each user signs a digital certificate and exchanges certificates with all other users. 3 PKI trust models use a CA, certificate authority: the hierarchical trust model, the distributed trust model, and the bridge trust model. Hierarchical trust model. The hierarchical trust model assigns a single hierarchy to one master CA called root. Root signs all digital certificate authorities with a single key. This model can be used in an organization where one CA is responsible for only that organization's digital certificates. Hierarchical trust model limitations. A single CA private key may be compromised, rendering all certificates worthless. Having a single CA who must verify and sign all digital certificates may create a significant backlog. Excuse me. Dry throat. Distributed trust model. The distributed trust model has multiple CAs that sign digital certificates. This eliminates limitations of hierarchical trust model. So basically, it's like the hierarchical, but it adds the option of having multiple people that are able to sign digital certificates. Then bridge trust model. The bridge trust model is similar to the distributed trust model. One CA acts as a facilitator to connect all. I really think that was just supposed to be interconnect all other CAs. Facilitator CA does not issue digital certificates. Instead, it acts as a hub between hierarchical and distributed trust model. Allows different models to be linked. So basically the whole point of bridge trust model is to bridge between two different models. Managing PKI, certificate policy. A certificate policy is a published set of rules that govern operation of a PKI. The CP provides recommended baseline security requirements for the use of and operation of a CA, RA, and other PKI components. Certificate Practice Statement, or CPS. A certificate practice statement is a technical document that describes in detail how the CA uses and manages certificates. It also covers how to register for a digital certificate, how to issue them, when to revoke them, procedural controls, and a key pair management. Okay, this is the certificate life cycle. Yeah, I know that's another problem, is those nice acronyms. CPS does not always mean the same thing. Okay, so certificate life cycle. Creation occurs after your user is positively identified. Suspension may occur when an employee is on a leave of absence or gets fired or anything like that. Revocation, certificate is no longer valid. Expiration, the key can no longer be used. Okay, key management, key storage. Public keys can be stored by embedding them within digital certificates. Private keys can be stored on users' local system. Software-based storage may expose keys to attackers. The alternative is storing keys in hardware. That's where you get those smart cards and the little tokens that you can use. Key usage, multiple pairs of dual keys can be created. One pair is used to encrypt information and the public key backed up in another location. Second pair would be used only for digital signatures, and the public key in that pair would never be backed up. Key handling procedures: escrow, expiration, renewal, revocation, recovery, suspension, destruction. Okay, knowledge check. Which of the following is considered a non-secure place where PKI encryption keys may be stored? Smart card token in a digital certificate local system. Good job. Generally speaking, D, but yeah, depending. Let's see, you said, yeah, smart card. Yeah, I could see for the Army that might be a problem. For the Army, any of them? Yes. Cryptographic protocols. Okay. The most common cryptographic transport algorithms, remember how we were talking about data at rest and transport? So they're talking about transport algorithms, include SSL or secure socket layer, transport layer security, TLS, security shell, hyper transport protocol secure, SMIME, secure real-time transport protocol, and IP security. Sometimes that's called IPsec. SSL, this one you guys should have heard of. SSL is one of the most common cryptographic protocols. It was developed by Netscape in 1994. The design goal was to create an encrypted data path between a client and a server. It uses standard AES. SSL version 3 is the current version. TLS is the replacement for SSL. Versions starting with 1.1 are significantly more secure than SSL version 3. Current version is 1.2. A cipher suite is a named combination of the encryption authentication and message authentication code, MAC, algorithms that are used with SSL and TLS.
How are versions starting with 1 more secure than 3? I mean, this is just in my head. I think of third generation being more advanced than first generation.
It's because, yeah, it doesn't make sense unless you think of it's the first generation of TLS that is more secure than the third generation of SSL. Because TLS came later.
I guess I didn't read that right.
Yeah, because SSL came first, their version numbers run more than, so they're up to like version 3. So when TLS was created, it's on like version 1.2. So it's numbered differently. No, you're cool.
I was just saying my mind skipped completely over. Like it just saw the versions and not anything else attached to them. So for like to me it was all SS version 3.
You just saw 1. The 4, 3, 4, 1. Yeah, no, I get it. Next, we have Secure Shell or SSH. This is an encrypted alternative to Telnet, which is a very old protocol used to access remote computers. It's a Linux, Unix-based command interface and protocol. SSH is a suite of 3 utilities: slogin, SSH, and SCP. Client and server ends of the connection are authenticated using a digital certificate, and passwords are encrypted. SSH can be used as a tool for secure network backups. So HTTPS, so we started out with HTTP, but then it became pretty relevant for us to have to encrypt that as time came on. So there are 2 different ports. The original HTTP used port 80, and now HTTPS uses 443. The secure version is actually plain and sent over SSL or TLS. And then, let me see if I'm doing that, sorry. Okay, so HTTP is just basically plain text is how I kind of think of it, and the other one's encrypted. And the easiest way for me to remember is, and then it's just because I remember ports, HTTP is port 80, and then the encrypted one is 443. And we pretty much all the time now use that HTTPS. And if you see a website without that, usually it's a bad site now. So SMIME, Secure Multipurpose Internet Mail Extension, is a protocol for securing email messages. MIME is a standard for how an electronic message will be organized. So SMIME describes how encryption information and a digital certificate can be included as part of the message body. SMIME allows users to send encrypted messages that are also digitally signed. There's also SRTP, which is Secure Real-Time Transport Protocol. This is secure extension protecting transmission using real-time transport protocol. SRTP provides protection for VoIP or voice over IP communications, adds secure features such as message authentication and confidentiality for VoIP communications. IP security or IPsec. IPsec is a protocol suite for securing internet protocol communications. IPsec is considered to be a transparent security protocol, transparent to applications, users, and software. IPsec provides 3 areas of protection that correspond to 3 IPsec protocols: authentication, confidentiality, and key management. IPsec supports 2 encryption modes. Transport mode encrypts only the data portion of each packet and leaves the header unencrypted. And tunnel mode, which encrypts both the header and the data portion. Weaknesses of cryptographic protocols. Due to the complexity of networking, cryptographic protocols are notoriously difficult to design. While the mathematics and related security of basic cryptographic algorithms have been extensively studied, the same cannot be said of cryptographic protocols. Older cryptographic protocols were designed by networking experts and not by cryptographic protocol experts. The associated security proofs and to guarantee the correctness of cryptographic protocols are much more complicated than those of cryptographic algorithms. So do you remember me talking about how Internet of Things devices were not designed by people who were in regular IT, so they didn't think about the security and things like that? Well, these old protocols were not designed by cryptographic experts, so they were just designed by networking people, so they didn't work as well and were not as secure. So it's basically the same thing. Okay, which encryption protocol is used for email messages? SMIME, SRTP, HTTPS, or TLS? You guys are on fire tonight. Good job. Implementing cryptography. Cryptography that is improperly applied can lead to vulnerabilities. It's essential to understand the different options that relate to cryptography. Implementing cryptography includes understanding key strength, secret algorithms, block cipher modes of operation, cryptographic service providers, and the use of algorithm input values. Key strength. A cryptographic key is a value that serves as input to an algorithm. It transforms plain text into ciphertext and vice versa for decryption. 3 primary characteristics that determine the resiliency of the key to attacks, called key strength, are randomness, length of the key, and crypto period, which is the length of time for which a key is authorized for use. Secret algorithms. Keys must be kept secret. Does the same apply to algorithms? Would a secret algorithm enhance security in the same way as keeping a key or password secret? No. For a cryptography to be useful, it needs to be widespread. A military force that uses cryptography must allow many users to know of its existence to use it. Yeah, shh, it's a secret. Yes, good point.
Or they can just do what the army did, and instead of letting everyone know anything about it, they just give you this nifty handheld device that you plug in and load the keys.
Yeah, you're like, do as you say, not as you do, right?
Hey, we were just dumb monkeys. We can't be trusted to think.
Block cipher modes of operation. Okay. A block cipher manipulates an entire block of plain text, which is why it's called a block cipher. The plain text is divided into separate blocks of specific length. Each block is encrypted independently. A block cipher mode of operation specifies how block ciphers should handle these blocks. The most common blocks: electronic code book, cipher block chaining, counter, and I am gonna mess up that one, so I'll just call it GCM. Crypto service providers. A crypto service provider allows an application to implement an encryption algorithm for execution. Crypto service providers typically implement cryptographic algorithms, generate keys, provide key storage, and authenticate users by calling various crypto modules to perform specific tasks. Crypto service providers can be implemented in software, hardware, or both. Okay, knowledge check. Which of the following is not a primary characteristic of key strength? Randomness, uniqueness, key length, crypto period. I don't know why I can't say that one. So A, B, C, or D. Hint, it's the one they didn't mention. Uniqueness, exactly. All right, so that's the end for this one. Now, I have, since we did not go have lecture yesterday because of my migraine, we have one more module for the week. Either I can continue and do that tonight, or we can do it tomorrow night. It is up to you guys. What would you prefer to do? Anybody? Okay, as it'll be, it started at the normal time, so 5 to 7 is when we were doing the lab time, and these aren't very long modules. So it looks like, am I seeing that everyone wants to do tomorrow night? Yeah, I'm not going to be on Saturday. Everyone should take advantage of that 3-day weekend as much as you can, even if it's just to get a bunch of work done. Okay, so we will do the next module tomorrow night then. And oh yeah, have fun building your computer. That always sounds like way more fun than doing some of the other stuff. All right, I'm going to go ahead and stop the recording.